Hello, I'm Xiaowei. Welcome to the presentation of our paper, Procedural Roof Generation from a Single Satellite Image. Thanks for your time. Given a single image of your neighborhood, have you ever wondered what shape your roof is and that of others in your city? A lot of methods have been proposed to tackle this problem. A majority of them are using aerial images. Aerial imagery is of high resolution, however, the task is still not easy and acquisition is more local. There are works that also take in 3D information, for instance, LiDAR data as input. However, the processing is still complicated and acquisition is even more specialized. How about satellite images? Satellite imagery is globally available, but the satellite data has a lower resolution. Our paper focuses on procedural roof generation from a single satellite image. Here is a preview of our generated procedural roofs for an urban area. We render our procedural results on top of a satellite image. For a single satellite image, the task is more challenging. Why is this hard? As you can see, satellite images suffer from low resolution, shadows, occlusions, noise, etc. Moreover, with the rapid development of deep learning techniques, people can directly apply deep segmentation models to satellite images. However, even with the state-of-the-art segmentation models, the results are still not satisfying. The boundaries are noisy and are mostly incomplete. Our paper is based on several observations. First, man-made structures, for example, roofs, have regular properties. Roof parts are mostly rectangles. Roof parts are usually aligned, and the sides of the roofs are parallel. The second key observation is that the space of potential building shapes and roofs, called PBSR here, is compact. In our settings, we can practically capture more than 90% of buildings in our datasets by limiting the possible set of building shapes to I shape, L shape, T shape, U shape, Z shape, those 5 shapes shown in this figure. Additionally, more than 96% of roofs have shapes in one of our supported 5 roof types: flat roof, gable roof, hip roof, pyramid roof, and half-hip roof. The aforementioned potential building shapes and roofs, PBSR, is an approximation to represent all possible building and roof structure combinations. For this purpose, we propose a graph representation. Each node stands for a singular roof, and the edge shows the connections of adjacent roof parts. Here are some examples with the corresponding graph representations. For example, the rightmost Z shape of the building can be clearly decomposed into 3 roof parts. So the graph representation has 3 connected nodes. Further, we define PBSR based on fundamental type F and its topologies. F is defined according to the number of roof parts. T shows the different connections within F. By means of graph isomorphism and our data settings, we only consider I up to 4, which results in 8 shapes. Further, among these 8 shapes, T31, T41, T42, and T44 are possible but not common in the real world. Thus, the compact PBSR can be explicitly enumerated. Note, we can theoretically group the space of potential building shape families to larger values for I and count for any complicated actual building. However, as discussed previously, by limiting the possible set of building shape families to a rather compact number, we have already captured most buildings in our datasets. Inspired by these observations, we present an automatic procedural modeling approach to handle building footprint regularization, building decomposition, and roof ridge prediction altogether from a single satellite image. Our framework consists of 2 main parts. It directly takes the segmentation of an urban area as input. The building decomposition component partitions the building image according to a compact space PBSR. This results in a regularized procedural building footprint and a set of initial roof parts. Then, our roof ridge detection component refines the procedural roof structure by inferring ridge parameter values of roof parts. The final output is the synthetic procedural generation of the input area. The building decomposition component consists of 3 parts: the PBSR, a building shape family classifier, and a building family configuration recognizer. We create a synthetic building dataset based on PBSR to train a classifier that takes a building segmentation image as input to predict the building shape family type. Regarding the creation of a synthetic dataset, in order to handle noisy and irregular building footprint segmentation, aside from typical data augmentation techniques, we add different levels of noise to our clean, regularized synthetic images shown in this figure. Once we got the shape of building footprint, we need to find the procedural parameters of the building. Configuration recognizer builds on a library that includes canonical building shape instances. We ignore configurations that are affine transformations of others. Further, we split the image into grids and iterate parameters in the grid space. Thus, the configuration library is also compact. We transform the input building segmentation into a canonical shape by applying a series of image processing methods and then find the best matched building configuration based on the intersection of units. The roof ridge detection component also has 3 parts: PBSR, a roof type classifier, and a configuration recognizer. Given a building image, we first apply an edge detector to generate an initial edge map for the building. We crop the building edge map and achieve corresponding edge map for each roof. We predict the roof type by our classifier trained with our generated synthetic dataset, and then find the best roof configuration in a similar way. Moreover, for a building with multiple roofs, two roofed parts in this figure. An iterative process refines the roof parts. We begin with recognizing the roof family type for each roof. Based on the roof type probabilities, we design the main roof part. See EI2 in this figure. Afterward, we focus on iteratively refining the rest of the roof parts. We start by decreasing the overlap area by half each time. For each iteration, we predict the roof type probability and find the corresponding best match configuration until we find the best matching. We evaluate our outputs for both the building decomposition component and roof ridge detection component. In particular, for building footprint, we evaluate both pixel-wise correctness and structure regularization. For correctness, we apply accuracy, precision, recall, and F1 score. For regularization, we compute the interior angles in degrees for each vertex. Then we cluster corners of similar angles into groups. The regularization error basically has two terms. The first term is the normalized standard deviation of angles among groups. We also add the second term to encourage fewer and larger groups. With regard to the roof ridge evaluation, at satellite level resolutions, pixel evaluation for ridges is not suitable anymore. Thus, we define our own terms. We evaluate the performance in terms of correctness, completeness, and hit ratio metrics. Correctness represents the percentage of the predict roof ridge, which lies within a rectangle buffer around the ground truth ridge. Completeness is the percentage of the ground truth, which lies within the buffer around the predict ridge. Hit ratio represents how many of the ridges have been found by our method. This term also considers the relative importance of each range. Here are some results. As clearly observed, the outputs of our method are visually appealing, and our results significantly improve building footprint regularization in terms of regularization error. For roof ridges, our method consistently achieved better performance compared to previous method in column C. For example, hit ratio improved by almost 32%, correctness improved by almost 28%, and completeness improved by 45% for SpaceNet. Yet more, as demonstrated in the figure, our results are qualitatively preferable. We show our procedural urban generations for 3 large areas here from multiple satellite datasets: SpaceNet, Crown AI, and also Urban 3D. Although we support a very wide range of building and roof types, there are always exceptions. Currently, for styles outside of our assumptions, our method gives its best guess. Our method also assumes that a singular rectangle stands for one roof part. Therefore, as you can see in the second row of the figure, one roof part highlighted by a purple box is undetected. Our approach cannot handle non-also rectified satellite images as input, shown in the third row. In theory, our framework can handle these failure scenarios by adding more building and roof types to our synthetic training datasets. As a summary, our work is the first pipeline to handle automatic roof shape estimation given a single unannotated satellite image, making use of building footprint regularization, building decomposition, and roof ridge prediction. Our procedural output for the urban area can be used in many applications. For example, solar panel planning, heating, cooling, rainfall modeling. Our approach has several avenues of future work. First, we'd like to support non-rectangular roof types and non-also rectified satellite images. Also, we would like to explore deep learning-based approaches to generate edge maps for the roof types. In addition, we would like to reconstruct more roof details, for instance, reconstruct dormers, chimneys, etc. For more details, we refer you to our paper.